Okay, what are we talking about today? Today we are talking about sorting algorithms. Over the next 2 days, today, Monday, we'll be talking about sorting algorithms. The four sorting algorithms we'll be talking about is bubble sort, insertion sort today. And on Monday, we'll be talking about merge sort and quick sort, okay? Bubble sort is one of the worst sorting algorithms out there, right? But as we said earlier, it's important to know it because you could get asked that at some interview. You could get asked to implement bubble sort and explain why it's a slow sorting algorithm. So we start talking about sorting algorithms by introducing bubble sort. Before we get started here, let's actually just watch a short video on bubble sort. So I'll pause the video right now. The way bubble sort works is it looks at 1 and 5. It looks at adjacent values. It looks at 1 and 5, and it sorts them, right? It sorts 1 and 5. It goes to 5 and 4. It goes to 4 and 2. It goes to 8 and 9. And it goes back again. So each time it does a pass, it swaps adjacent values, sorts them, goes to the next value, right? Until the entire thing is sorted. Okay, so let's continue the video here. The music also stopped, sorry. It still checks to make sure that everything is sorted. Okay, so that is bubble sort, right? So it looks at from the beginning value, it moves, it doesn't check the beginning value because there's nothing to compare. It goes to value 2, it compares value 2 with value 1. If it needs to sort, it swaps them in place. Again, the big part there, it swaps the values in place. So it doesn't take up any additional memory. That's the one benefit with this particular algorithm. It doesn't take up any extra space, that's it. But apart from that, the runtime is horrible, as we saw there in the video. So with our bubble sort, let's write it down. Let's implement it here, just using a simple pseudocode. We'll use some values here. We'll use 10, 2 minus 8, and 4. So here we have an unsorted list of 4 values. We have an unsorted list of 4 values. We'll implement bubble sort to sort those values. So the first pass, we look at 10 and 2. So here we're looking at 10 and 2, right? Then we look at minus 8 and 4. Say that again?
It doesn't go to the next one right away?
Well, it swaps 2 values at a time.
I think he's saying doesn't
No.
it go to like 10 and negative 8?
Yeah, 10 negative 8.
Yeah.
So negative 8, right? But it's not going to swap negative 8 and 10 right now. Because currently, if we are J, let's start this over. Let's start this over. 2 minus 8 and 4, right? Currently, if my values are J, again, we don't look at 10, right? We're not looking at 10 as a comparison. So currently, we have a marker at position 2, right? Not position 0. So the 2 values I'm looking at currently is 10 and 2. Everybody with me? I'm looking at 10 and 2. I swap 10 and 2 because in this case 2 is less than 10. Do we agree?
Yeah.
Okay, so we go ahead and we swap that. So this is 2 and this is 10. So J now moves to 8. Do we see that? Everybody? J is the that marker that we use, the counter or the place value that we use in our array.
But isn't I now 110?
So J now is 8, right? So 8 versus 2 is, in that case, this is one pass. So we're looking at minus 8 and 10 in this case, right? So this is minus 8. Let's just write it down so we're not confusing ourselves. So J is here, and we'll go to pass 3. So now we'll look at 10 and minus 8. Everybody with me? Everybody with me? We look at the value before. So in this case, 2 is fine. So 10 and 8, we will swap 10 and 8. And where's J now? J is at 4. Okay? Is our array sorted? No. No, so we still have to continue. Let's just write out all our values again. So here we have J. Is minus 8 less than 2?
Why is J back at 8 instead of at 8?
Every time we come back in the loop, J is started at the first value.
Like
The second value, not 2.
Oh,
Okay?
Why
Yes.
did it swap 10 and 4 if it was at 4?
Why didn't we swap 10 and 4? Here?
Shouldn't it be 2 negative 8, then 4, then 10? If it's at
Yes,
4.
yeah. Sorry. Correct. Because we swap in 4 and 10. Very good. Okay, excellent. So at this point, we at minus 8, and we agreed that minus 8 is less than 2, correct? Okay, excellent. So here we'll swap minus 8 and 2. Where is J now? J is at 4. Great. Is 4 less than 2? No. So let's just go ahead and increment J. J is 10. At this point, we need to look at all our values again before we say we're done. Okay? We can, yes, we see we're done, but we still have to go through each value again, as we saw in that video, to confirm that we do have a sorted array. Everybody with me? So we'll write down all our values again. We start off with J here. Is 2 less than minus 8?
No.
No. So let's increment J. Is 4 less than 2? No. So let's increment J. Is 10 less than 4?
No.
So at this point, we are done here. And here we have our sorted array. Right? So this is what we sort, done on paper here. And now we'll go ahead and we'll implement it in code. But the big takeaways here, there was no point we created a new array or something to keep track of that array. Or not to keep track of that array, but we did not create a new array. The way we change the values is swapping the values. Okay? The way we change those values is by swapping the values. There's two ways we could swap the values. One way we could swap the value is using the built-in swap function in Swift. In Swift, there's a built-in swap function. But I've heard that in interviews, sometimes people are like, oh, maybe, how can you do it without using the built-in swap function? Everybody with me? So here, if we're not using the built-in swap function, we have to use something we've used before, have like a temporary variable to keep track or to save the value before we go ahead and overwrite that value. Everybody remember what we did with the temporary variable we had before? So basically, we had like a temporary variable, let temp variable equal to, call it value 1. And then we could go ahead and override value 1 with value 2, right? and then we'll say value 2 equals to what?
So whatever new value you want.
Temp,
Okay.
right?
Oh, okay. Wait,
Right.
why?
Because value
Oh,
1,
swap the values.
exactly. So there's swap, which is the built-in function, and there's doing it by hand, not by hand, but by doing it without a built-in function, okay? So if you were asked to implement this without swap function, you would do it with option 2, which we'll do today.
Swap is for arrays or?
Yeah, arrays, yes. So it would swap the indices.
Something like this before, I think.
Yes, we did it in one. I can't remember exactly what project, but we did it somewhere before.
Not in the project, I think when we were learning, like, these, stuff like this, we did this before.
Yeah.
It was, I think it was,
Was it linked list?
I think it was like this, when you had to make it equal to you had to save, you wanted to save that, that so it doesn't change when you can't get it back, you had to save.
When we're changing the pointers on the linked list? Yeah, very good. Okay, so again, this is bubble sort, and we'll be writing our own swap logic. We won't be using the built-in swap logic, right? So maybe we use the method option 2, but for insertion sort, maybe we just use the built-in function. Everybody with me? But at the end of the day, please know if you are asked, write the algorithm without using a built-in function swap, know how to do it, right? Because at the end of the day, what we want to do, for example, if we want to swap two values, we want to swap, let's see, two values here, those two values. If we want to swap those two values, we could use swap built-in function, or we could use a temporary variable. Everybody with me? Okay, cool. Any questions so far with what we did?
Swap function will do sorting of the whole
No.
array or just one?
No, just the change. Like if I see a value is smaller, like if I see a right value is smaller than the left value, I want to swap those two values. So what the array swap does is on an array, there's a swap function. I could say swap I with j. So it would swap those positions, the values, okay? So if the values were, for example, 4 and -8, it would swap them such that it's -8 and 4 in that array, at those positions. Yes, which will have a position. We'll have a position, let me actually write that out. We'll have a position j, and we'll have a position j -1. Right? Cool? All right, so let's go to code. Any questions so far with what we did here again by hand? Any questions? All right, let's go ahead and implement it. So we're creating the playgrounds. Create a new playground and simply call it bubble sort. Again, everything we're doing, please push it to GitHub, have reference to it, because we'll be seeing a lot of things. So not even just for the assessment, but as you start prepping, when you get closer to job search, there's certain things you just have to review before you go to an interview, right? And most likely you'll be asking the interviewer like what you should be reading up on. They'll give you a good job, will give you a set of resources to study up on, right? So as I tell you, searching algorithms, know your sorting algorithms, then you would make sure that as you're going into that interview or whatever, that you read up on bubble sort, you review bubble sort, you review the worst ones, the best ones, and all that stuff, and know the pros and cons. Because the big pro here, what's the big pro that we've been talking about? It's in place, right? It's in place, which is constant, which is awesome. That's the one pro there with bubble sort. Dark, large. Okay, so what are we doing? We're doing bubble sort. It's a sorting algorithm. The runtime of bubble sort. Worst runtime. When we talk about runtime, again to reiterate, when we talk about runtime, we always talk about the worst case scenario. What's the worst runtime of that particular algorithm? We're not looking at the best runtime. We're looking at the worst runtime. Here, the worst runtime is big O of n squared, right? Or quadratic. What's the space complexity? If it's in place, the space complexity becomes constant because I'm not using any additional space for that algorithm, right? So the space complexity is constant. I'm sorry?
Should we continue this from Q's or make it
Make a new one. Just keep them separate. Don't put them in the same playground. So at the end of the day, you'll be pushing a separate project of playgrounds. What you could do is create a DSA folder or DSA repo and add your playgrounds to that repo and then keep pushing that DSA repo. Everybody with me? Cool. So space complexity we said here is big O constant here, and Y, it's sorts in place. And then whenever we see sorts in place, think of in-out function, right? We got exposed to in-out functions before, right? But when you hear, if anybody tell you to solve some algorithm or solve some problem where it's in place, automatically you should be thinking my function signature should have an in-out argument or parameter, okay? Questions about that? Okay, cool. So let's go ahead and implement it based on what we just spoke about, what we just wrote. We'll start off with a function. We'll give it a name. We'll say it's bubble sort. What input are we expecting? An array. Very good. So here we're expecting our input to be an array. We'll just say an array of integers. We could make it generic, but here we'll just say it's an array of integers. And we said our function, we said our sorting algorithm is in place. So what are we doing to our function here? We're not returning anything, right? That's the big point to get home here. If we sort it in place, we are not returning, we're not returning a new array here. We're not returning the new array. So how does that array get manipulated? That array gets manipulated via my in-out function, right? As we got exposed to in-out functions, I have an array as input. The way I change that array is via the in-out function. So that function here, the function is going to have a reference to the array that you passed in. So I'm able to manipulate the array in place. So as we do our swaps, the swaps are happening on that array that got passed in, okay? Christian?
Yeah.
So we're not returning. Basically here, we need to say in-out. So the minute I say in-out here on my function, now I have a reference. Remember references, class types there? If I have a reference, I could change the value of something, right? If we all have reference to the same whiteboard, we could all annotate the same whiteboard, okay? So here my function has a reference to that array. It could change that array outside the function. Yes?
So that just basically says, is the in-out saying like what I'm putting in, give it back?
The input I got in,
Yeah.
I'm able to change that input.
Right, so what I'm giving you, I'm changing it, and I want you to give me exactly what I gave you. I'm giving you a copy of it. I want the same thing. Is that what you're saying?
Not even a copy, it's a reference, the same reference.
The same
Yeah, it's not a copy at all. It's
don't give me a copy,
yeah,
I want the same.
the same reference. We're not creating a copy here. A regular function would have a copy of an array, but this one, like for example, our whiteboarding yesterday for Qs, everybody, For the Q's, if we needed to manipulate that Q input, the Q input we had to create an internal variable, correct? Because it's a let, because it's passed by, it's a copy, I cannot change that outside of it. So I had to create a variable for it. Cool?
But in this case, you can use a let and still manipulate it.
Exactly, because it's in out. Because it's in out. I have a reference to it. Very, very good. So here our function signature is pretty much good to go. The big important part there is in out. In out implements in place. So in out indicates in place. Manipulation. Cool? Great. Okay, so now let's go ahead and start off the algorithm. So we'll start off by saying for 0 dot dot up to the array dot count. I'm not including the last value in that array or the count of that last value. If my array is 4, if the count is 4, I'm not getting to value 4, because that'll be out of bounds, right? So that's a closed range. Do we remember closed range here? It doesn't include that count value, right? So next up, we'll use the same j value we had. So we'll say for j in 1 up to array.count. And again, position 1, because we're not looking at position 0. Everybody with me? When we were comparing, if we go back to our diagram here, when we were comparing, for example, in the first place here, 10 doesn't have a previous value. Everybody with me? 10 does not have a previous value. So I'm not comparing 10 with no previous value here, if I'm looking at number 1, right? I'm moving out to position 1, then I could compare 2 with 10. So that's why we start off with 1 here in our algorithm. Let me just put this right by that guy. Cool? So this is why we have 1 here. So every time I go back and check, I'm starting from 1. Everybody with me? Okay. Now we're in our inner for loop, and to keep count here, the runtime of my outside for loop is big O of n. The runtime of my inside for loop is big O of n. I'm going through the same collection twice. Everybody with me? It's the same collection. What's this collection here? It's the array, the input array. What's that collection? It's the input array. I denote it by n, right? Number of elements in that particular collection is n. If I'm using a for loop, I'm going through it n times. N times n is n squared. So that's why we come up with this algorithm here. As the worst case scenario, I have to go through each element n times twice. That equals to n squared here. Now we want to do the comparison. We want to say here, if array at j is less than array position at j minus 1, we'll pause here. This is the same calculation we did earlier. When we looked at j, what did we look at? We looked at j minus 1. If we go back to our diagram here, if I'm looking at j here, everybody, j, what's j minus 1? 10, right? Everybody with me? Those are the two values I'm looking at. I'm looking at those adjacent values. If I'm at j, I'm looking at j minus 1, which is 10. Cool? So this is the algorithm for seeing if j in that case is less than j minus 1. If it is, then we want to do what?
Swap.
We want to swap, right? So if we come into this block here, then we want to swap. And here we'll implement swap without using the built-in swap function. The built-in swap function would look like this, right? So we have array swap, and here we see swap at, right? So swap at expects 2 indices. Do we see that? Cool. So we'll be doing a 3-liner as opposed to using this built-in function. So we'll start off by saying let temp equal to, I'll save one of the values. I'll save the value at j, and now I could override it because I've saved it. I've saved that value, now I could override it. So here we could say saved the value at array j before overriding. So we saved it before we override it. Now we could override it with j minus 1. And lastly, we need to say position at j minus 1. What does this equal to? Temp. Very good. So that's it. Our algorithm is basically done. All what we need to do now is to test it. We could test it with the same values we had earlier. We could create a list. We had 10, we had 2, we had minus 8, and we had 4.
Can we print it each time so we see it happen?
We could print it after the fact. Yeah. So
Print a lot of loops.
yeah, you could print. You could print. So here now we have our list. Let's call our bubble sort. And if we look at the call for bubble sort here, we have an ampersand or the and symbol, right? Right before the array, the int array. Do we see that? Because now it's saying it has a pointer. If you call in this, you have to specify the ampersand before the list name. What does that mean? I'll press enter. You need to specify, I have a reference to list here. By using the inout, again, if I'm using inout, when I call my function on my list, it needs to be a variable. If I say this is a constant, I'll get a compiler error, right? Because here I'm saying I want to change list, but list is a constant. I cannot change list if list is a constant. Yes?
The array has a negative number and it's a closed range between 0 and the count. What's that? Okay,
Do we have to create a copy?
No, we're not creating a copy. I'm just showing us, illustrating to us like compiler errors here. So if we have a constant, we cannot change list. Because if we have to change list needs to be mutable, right? So for list to be mutable, it needs to be a var. Go ahead.
No, I'll let you finish first.
Ask a question before I continue.
I thought that, I just asked that if it could be a let and we manipulate it.
Not here. It cannot be a let here. The question you were asking, I thought it was referring to yesterday, where we had our Q parameter being a let, because by nature, a parameter is a let by nature, right? Without specifying it as being inout, right? So like yesterday, we had some questions such that we had a function, for example.
Mark the array itself as a let because it still has to be manipulated, but inside.
Outside here, yes, exactly.
You can manipulate it because sometimes it would tell you like it's a let constant, Okay.
Exactly. Like yesterday, we'd have to use a var inside that function. Okay, cool. Very good. Kristen, you had the next question?
Sure.
You had the next question here? Okay, so here we need to be a var here, then we have our reference to list, and then list could get changed inside that function. They're different names, but it's the same reference. Everybody with me? Everybody with me? All right? Okay, cool. So now we could simply print list and play the playgrounds here. And here we should have our sorted list as being -8, 2, 4, and 10. Everybody with me now? Right? Did we all get that expected result? Sorry, Luba? Let's double check what we're doing on line 12 here, because line 12 is pretty much the important part. Plus, let's see what we're doing in our temp changes.
Oh.
It's sorted descending.
Sorted
Descending. Okay. I mean, we could go further. We could have like a closure that takes in some sort of sorting algorithm, and then you could say if I want to sort it ascending or descending, right? Yes.
When you wrote it out earlier, I think you did like 2 extra lines that I really thought to do.
No, we did more lines so we could just illustrate it. We rewrote it. I didn't want to. That's why I did that.
But you skipped, you jumped 2 spaces for the second line. Just when you drew it out.
What number are we talking about?
Because I printed it out and it was a 4 line.
We did extras. We did.
Oh.
We reprinted it out so that we could have gone through it again. Okay.
If you print it, it really does show you how it switches each one. I printed it inside of the type of function that shows you each time it switches.
Very good. Okay, so again, keep this close to us. Know 2 things to walk away from bubble sort knowing. One is the algorithm sorts in place. Know what that means. 2, the algorithm is one of the worst sorting algorithms we could find, right? Cool? So those are the 2 things to walk away with.
It's slow.
Yes. Worst case, we saw what it was or what it looked like in the video, right? It goes through each element multiple times, right? Even when it's sorted the last one, it still has to go through it again to make sure it's sorted.
Yeah.
Okay? Cool. Any questions before we move on? Yes, sir.
So, at a minimum, it's gonna have to run twice.
More than twice.
As many times
No,
as
I mean,
you
like,
have
everything
numbers.
is sorted.
At a minimum, you mean like best case?
Yeah.
Best case, it finds it right away,
Okay.
right? Like, but still, that's not what we're looking for.
But it's also go through for each.
I mean, best case, it's sorted, sorry. Best case, the array is sorted already. But it still has to go through it once, which is n. So best case is n there. Does that make sense, everybody? So Craig's question, like, what's the best case? Best case, the array is sorted, but I still need to go through that array to make sure it's sorted. Does that make sense?
Yeah.
All right, very good. So let's stop